Okay, so my talk today is about Elm. How many people know what Elm is? I've heard of it. Not too much. How many people know what functional programming is? Okay, almost everyone. Who has done some functional programming? Okay. It's more than I thought. Well, Elm, yeah, some of you know it, but for the rest who don't, Elm is a purely functional programming language. It's created by Evan, in 2012, and well, Evan is sort of like the Guido van Rossum of Python. He's the benevolent dictator for life. Evan is the benevolent dictator for life of Elm. He's the creative mind, and he makes the decisions behind it. It's a language Elm is a language that compiles to JavaScript. You can make a web browser, a graphical user interface in it. Okay, yeah, next one. So why yet another language? This is the Tioga Index. The Tioga Index is an index that measures how much programming languages are used around the world. And these are the first 10 languages that are in there. These results are from May 2017. And I don't know if you see what's the same thing. See the repeating pattern in here, but all 10 are primarily imperative languages. And actually, there are 20. They publish a list of the top 20, and 18 out of the 20 are imperative languages. I don't know if you can count R as an imperative language, but then it will be 19. So why is that? Why are all the top programming languages are used? Why are they imperative? Is there something special about it, or why don't we use other kind of programming paradigm languages? So yeah, well, most of the languages that I work with or have been taught in the past in my life were imperative programming languages. Until a year ago, a colleague of mine, he recommended Elm to me, and he said, well, you should look at it. And I started with it, and I was amazed because it was totally different. Everything you kind of have to unlearn everything you know from imperative programming. So what I want to share with you today is I hope to inspire you to also try it, to try something different. Because it's a great quote from Alan Perlis. Not many people know him, but why should you learn a programming language like Java or C or Python? Why should you learn another imperative programming language? Because it's actually, you just do the same things in the same way. It's better, I think, or it's good to learn new programming paradigms, to do things differently. And by doing things differently, you can use that in your daily work and to your benefit. Okay, so a short agenda. First, I will talk a bit more about functional programming. Most of you have heard of it, so I will keep it short. Then I'm going to show you what Elm is, how it looks like, by giving you a few examples from how code looks in Python, how it looks imperative, and how you would do it functionally. Then I will tell you a bit about Elm architecture, because the Elm is nice, but you also want to build applications with it. That's where Elm architecture comes in. I will give a short demo. Actually, I will intertwine that a bit. I can't use my own laptop, unfortunately, but I can show some demos. I will then recap with a list of the superpowers, the things that are really different about Elm, and that make it great. And finally, what will be the conclusion. So functional programming. Well, this is a definition from Google, actually Wikipedia. I thought, well, they can do it better than I can. And the thing that what I find the most different about functional programming, and the most important compared to imperative programming, is that in functional programming you avoid changing state and mutable data as much as possible. Actually, when you have a pure functional programming language, you don't do any mutation or changing state at all. And Elm is a purely functional programming language. So that sounds nice. It makes your programs easier to reason about, but a really purely functional programming language in that you can't do anything else but heat up your processor. You don't have any input or output. So yeah, well, what's the use of that? I will get back to that later. Another, I think, important aspect of functional programming is the definition of a pure function. So that's a function that is only dependent on its input. The output of a function is only dependent on the input arguments. So if you call a function with a certain set of arguments, it will always return the same value, no matter what time, what date, in what place, or what state. It doesn't matter. That it can't access any state beyond that function. I've lost my slides. One moment. Okay, next. So then Elm. Elm was created by Evan because he noticed that functional programming, it promises a lot of good things, but nobody uses it. We saw it in the Tioga Index. It is not even in the top 20 of the programming language. So why is that? Well, I think it's because programming languages are perceived as being academic and hard to learn, and I think the best example of that is Haskell. The entry level is really high. It's really difficult to get started with. So that's why Evan created Elm. Elm is targeted at JavaScript developers. It has an online environment, which I will show in a moment. It's really easy to get going, and he dropped a lot of, actually it's kind of a subset of Haskell, so it's primarily the base language from that, ML, but he dropped a lot of the really difficult stuff about Haskell. So it doesn't have any monads, it doesn't have type classes, and all the things that are difficult when you come from imperative language like JavaScript. So it makes it much easier. Okay, so now some examples. Say you want to define a function that you give it a list, and it will increment every element in that list. It's a list of integers. It will increment every element of that list by 1. Well, this is how you would do it in imperative Python, or it's one way to do it, of course. Okay, so how would you do it in functional Python? I guess you guys know that. You would use a map function. You give it a lambda function that will be executed on every element on the list, and you will get back a new list that has every element increased by 1. So actually, this is pretty straightforward. You can pretty much translate this to Elm. It's a bit different kind of syntax, but you say we have a +1 function, you give it an argument, it's named LST, list, and you call a list.map function, and you give it also a lambda, the /x in there, that's a lambda function, and you pass it the list. And well, actually, these things that they look so similar is because a lot of the functional of Python borrowed a lot from functional languages in the years that it has developed. So this is the straightforward Elm solution. There's also a bit of more advanced syntax, but I won't go too deep into that, but it's shorter, you see. Next example is for lists. Say you want to get the first element of a list in Python. Well, it's pretty obvious, it's basic syntax. Excuse me. So when you give it a list, it will return the first element. But what if you give it an empty list? Then it will give you a runtime exception, an index error. So yeah, you can build a function that will work around it. But the nice thing about Elm is that it doesn't have runtime exceptions, practically. Because if you would ask the head of a list, then if you give it a list with integers, it will give you back just 1. And that's a wrapper around the value that you will get back. And it means that it has found an element that is 1. Where in a normal programming language you would say, you would just return 1, and then like in Python, and when you give it an invalid argument, it will return null, or it will throw an exception, or whatever. You can't do that in Elm. What you can do in Elm is you can give back nothing. That's also a kind of wrapper. The nice thing about this is and I will show you in a minute, is that if you write a header 0 function and you would leave out the nothing case, so in the case the list is empty, it will give you an exception and it will say, well, you forgot to handle the nothing case. This is also a bit more advanced topic. I don't know if anybody of you use this in your daily work, but you can do it in Python. It's called currying. With currying, you can define a function and you what you basically do is, instead of, say you have a function append, and it will append 2 arguments with space in between, what you can do if you make it a curried function, then you can partially apply that function. So you can give it an argument of hello, like we do here, say hello is append curry hello, and then you will get back a new function, which will, when called, then execute the actual function, the append function. So you can not only use the function as a whole, but you can use parts of the function. And well, where the real power of that comes from is if you use, for example, we defined say hello there, and you can use that partial function and you can apply it to a list, to a whole list of arguments, and then it will map say hello on each of those. Okay, I will not go too deep into this because I will give a demo shortly. Another thing about functional programming, because you aren't allowed to change state or to mutate data, so you aren't allowed to, say, for example, use a for loop and have an I variable that you will mutate. You will say I is 0, I is 1. That's not allowed. So how then would you do? How then would you loop over a list? Well, for that we have recursion. On the left is an example of the map function I used in previous slides. And example definition of how you would do it in Python. You would say for element lists or something like that. But that actually keeps track of some state. On the right is the function definition of how you would do it in Elm. And as you see there, it's really, I think it's really straightforward. I don't know what you guys think of it, but it's you when you're given a list and the list is empty, it's the first case, then you would just return an empty list. Where you get a list that's not empty, and it's a special syntax, you would decompose the list into a head and a tail, and you would evaluate the function on the first element of the list, on the head, and you will return that, and then map on the tail. You would call it yourself recursively. And by that, you can map the entire list. Okay, well, the Elm architecture. So this was all really nice. But like I said before, if you use pure functional programming, you can't have any side effects, so it's only good for heating up your processor. So we want to show something on the screen. That's where the Elm architecture comes in, because remember Elm is only pure, so how then would you show something on the screen? Well, that's the secret of Elm. It has a runtime, and that runtime is allowed to do side effects, but your code is not. So the only thing you can do, you can write a view and an update function, and what the Elm runtime does is you give it a model of your state, and it will call the view function on that. It's kind of like React and Redux. And the view function will make a DOM tree, will render the HTML for the given model that you have at that moment. And well, then when the user clicks on something in the browser, for example, and then the Elm runtime will send a message to the update function, and it will give the update function the message and the model at that moment, and the update function will return a new model. And that model will be given to the view function. It will give back HTML, and the browser, or the Elm runtime with the browser, will loop through that. So these are the, this is how it would look like in code. You define a model. Remember, this is a typed functional language, so you have to define types for some things. You define what kind of messages are allowed in your system, and you define an update and a view function. Okay, so now I will give a short demo of how you would make a simple application with this. Let's see. I hope it works. Okay, so we start with importing some stuff. We need the HTML library. Okay. Now, like I told you, we need a model. So let's say for this use case, we want to make a counter. Really simple. So we define a model, and the model is just an integer, really basic. Then we need a message, and the message is we want to be able to increment the counter or you want to be able to decrement the counter. Okay, so now we need an update function. Update was given a message and a model. These are variables, and depending on the message, let's say it's increment, and then we say model plus 1. We return the model plus 1. Really simple. We need a view function, and the view function is, we render it as a div, and it has a h1. This is really just a syntax that will generate HTML. Let's call it a counter. And we give it a span here with text. And here we render the model, or that's the integer. Okay, now we're going to compile this. And it will say, well, this is what I told you about the case statement. Every message type that's defined here, yeah, you see the cursor. We say message is either an increment or a decrement, and I forgot to implement the decrement here. That's what the compiler is telling me now. So okay, I have to implement the decrement. I will do that too. Now we need a bit of plumbing, because this doesn't do anything. We have to specify that beginners program. We have to specify Elm what our update function is, and we need to initialize the model with something. We need to say we start with 0. Our update function is this. Our view function is this. Now it says something about white space. I think that one. And I made a typo there. You see, this is a nice thing about Elm. Every time you make a mistake, the compiler will say to you, well, this is the mistake you made. I think you mean this. And well, then this is the counter. It's still at 0. We need buttons, of course, to do something with it. And then we say on click. If we click on this button, we send the message increment. We give the button the text plus. And then, well, I can compile again, show you the error. We haven't defined on click. Events on click. We compile it. I don't know what this means. There it is. Oh, now we can increment the counter. And of course we need the decrement button, but that's really straightforward. Okay, there. Now we can decrement. Oh, yeah, of course, I forgot to. Too much copy pasting. Now we can increment and decrement. Okay. So this is really just a basic example, but I hope it shows how easy it is to get such a simple program in Elm going. And the nice thing about it is I can't show it, unfortunately. It was on my other laptop. Because every state transition, it's done by the update function. When the update function gets a message, it will update the state, the model. There is a special, it's called a time-traveling debugger in Elm. It will keep track of all the messages that are sent by your browser to the update function, and what it means is you can go back in time. You can just start this, and you can click on plus and minus, or you can imagine when you have a really complex web application, you will go through some forms, and then, for example, there is an error. You can track back all the state changes that have happened since then. And the really nice thing is that you can even make a JSON export of that, and you can send that to your customer support or something, or a client can send that, and you can reproduce the exact same state at which the client saw the error. That's really nice. Okay, not that one. Let's continue with the presentation. Yeah, that was the demo. So this was really simple. There are, of course, this was a basic side effect. The basic side effect is rendering the HTML. But what about more complex side effects? And with complex side effects, I mean doing an HTTP request, doing something with WebSockets, local storage, time. Even time is a side effect, because how would you get time out of a pure function? You call the function with 0 arguments and you get an integer back. How can the output of that function be only bound to the input? It can't be. It has a side effect. And of course, there are not only output commands, but you also have input. The outputs in Elm are called commands, and the input is called subscriptions. Inputs can be things like the user moved his mouse or pressed the key on the keyboard. Something over WebSocket got in. I don't know if this is readable. It's a bit complex, this graph. So I will not explain everything, but I think the important thing about this is that in the center, the blue rectangle, that's where your Elm code is. That's the pure world. Inside that, you can't do anything, you can't have any side effects. The only thing you can do is you can generate from your view function, given your model, you can generate HTML, and you can ask the Elm runtime for please execute this command for me, and when it's done, send a message back to me. That's the other side. Or you can say, I want to be subscribed on when the user clicks somewhere, or when they got something over WebSocket. But that's all you can do. You can't say in there, I want to save something on local storage. You have to instruct the Elm runtime to do that for you. That one I can't do, unfortunately. Okay, so to quickly recap, and some other things here that I haven't told you about. I call these the superpowers of Elm, or superpowers of functional programming. For example, Elm is statically typed. So the superpower there is that it's simple to refactor, and you can be confident about refactoring. If you refactor something in Python, yeah, well, you don't know. You just run it, or you can do Control F and search through your whole code base, and you don't know if something is broken or not. You will hear about that from your customers probably. In Elm, the compiler says no, and then you have to fix that. You have controlled side effects. Your code's easy to reason about. When you get when you see a function in the library and it's I don't know, it has no input parameters, or it can't. So say it has one input parameter, you give it an integer and it gives you the double of that integer back. It's a really simple function. When you're living in a purely Elm world, you know for sure that that code can't launch the nuclear missiles, it can't do an HTTP request, it can't have any side effects. And that's really nice. I mean, in Python, if you call a function, you don't know what it does. I mean, it can install a keylogger. It can do anything you want, anything it wants. Of course, limited by your operating system, but still. Elm has no runtime errors. That's the really, really statically typing. You can't compare it to Java. Java has a weaker kind of type system, and that's why it does have runtime errors. In Elm, you don't have any. Well, it doesn't have any monads. That's nice to get started with. It's easier to pick up. Elm has enforced formatting. If you press Ctrl S, then it will automatically format your code according to a one standard. There's just one standard of how Elm code should look, and that's what everybody does. No finicking about friendly error messages. I don't know if you saw it in the presentation, but or during the demo. The error messages that the compiler gives are really useful. It really helps. It doesn't just say, I don't know HTML.beginners function. It will say, I don't know that function. Do you mean HTML.beginner function? It will actually help you write your code. And finally, pure functions. This is a bit controversial, but in theory, it could be faster than JavaScript. It compiles to JavaScript, but because Elm uses pure functions, you can use some optimizations. It's really easy to use optimizations because you know that the function will always return the same value given an input value. You can optimize that away. For JavaScript, there are tools that can do that, like prepack, but it's really, really, really hard to do that. In Elm, it's really, really simple because you know it doesn't have any side effects, so why not just cache it, or why not memorize it, or why not just refactor it away, or optimize it away when you compile it. Okay, finally, it's not a religion, although I may make it sound like that. I think it's really good to, from time to time, practice what you know in a different language, in a different environment, with different conditions. And I think Elm is really the perfect language for that because it forces you to drop the mutation of state, and it forces you to use the Elm architecture. You don't have a choice. Do you want to use React or, I don't know, Mithril, or you have a ton of libraries that you can use when you want to build a JavaScript user interface. In Elm, it's just the Elm architecture. You're stuck with that, but it's good. And I would encourage you to try this and try other programming languages paradigms. Like Alan Perlis said, it's not worth learning a new language that does the same things that you already know. Learn something new. Okay, some quick tips on where to get started. What you just saw me doing during the demo, you can try that online. It's elm.org, elmlang.org/try. It's not in there. I will put it in there. It's just an online environment in which you can really easily try it out. All right, on a side note, we're hiring, of course, like everybody here. So if you're interested, please talk to us afterwards. Well, that was it. Are there any questions? You first? Yeah, sorry. One moment. Yes, you can, but because they can have side effects, you have to talk to them through what Elm calls ports. So you have to define typed signatures for everything you want to do to JavaScript. So actually, you can do it, but it's really hard. For some JavaScript libraries, there are interfaces, but the general consensus is just don't do it, just write it in Elm. So. Haskell has a lot of libraries for literally anything, but Elm doesn't. That's true. I see Elm more as a sort of a research. It's fun to do. It's nice to make some applications in it. There are some companies who are using it in production, but not many. And I think it's just good as a toy language. It's good to make tiny user interface with to get a feeling for functional programming. When you really want to make a good functional, when you really want to pick a good functional language for production, I'm looking at ClojureScript at the moment, and I think that's a really good contender. It does have the ecosystem. It does have the easy JavaScript interface. It has Clojure as the backend language. So I hope that answers your question. Yes?
How do you store stuff in the database?
This is purely in the front end. So you would do a HTTP request or a WebSocket request, and in the backend in Python, whatever you can store it. Yeah. Yes? What other kind of projects?
Yeah, like you said, the UI is well. I can imagine that like you wouldn't want to program a game in a functional language because you know you need a lot of states change. So I imagine that some projects are better suited for functional languages than others.
Yeah.
Can you give a few examples of projects that are well suited for functional languages?
It's a hard question. I think you could even make a game in a functional language, but the harder thing is that, like in Elm, you have the update function that will handle all changes. So when you make a game or something in a functional language like Elm, in purely functional language, all your state changes have to be done by the update function. But it can delegate some of those messages to other parts. So you can build complex systems out of it. But yeah, I don't know if it's the best choice. That's true. Mm-hmm. Yep, that's true. Yeah.
And I saw VDOM diff change.
Yeah. Yeah.
So in terms of games, say I have a gigabyte of states, all my players and where they are and where.
Yeah, you wouldn't want to do it with a virtual DOM, no.
No, if I have to output a gigabyte every 24th of a second.
Yeah. No, that's true. I don't know how well it scales. I mean, Facebook's using React. It's basically the same model. Elm says that their virtual DOM implementation is faster, but I don't know that for sure. But apparently it can handle Facebook, so pretty big user interfaces it can handle. Yeah.
So in your small example with the counter, how did Elm figure out the signature of your update function?
Yeah, that's actually a good question. It has really good inference, type inference. So it will figure that out.
Because if that increment is new, it has to be a message, and therefore there has to be a vector as well.
Yeah. Yeah, it's a good question. I don't know for sure where it would infer that message. Yeah, I think I know. Because I'm using increment and decrement as the message, it can infer. Those are both subtypes of subtypes, instantiations of message. So it will infer that that's the type signature. Yeah, it's all types in Elm have capital letters, and yes.
Well, if I would have an additional type, let's say message 2, which is an increment, decrement, or something else,
Yeah.
I would no longer be able to infer the type, the signature of.
Yeah, that's correct. Yeah, then you have to specify it, and that's actually not really difficult. It's in the slides, but it's good practice to first type your type signatures and then make the implementation. But well, I thought it may be a bit too much to show all the type signatures here. Any more questions? Okay, well, thank you.
Yeah, and thank you. It was a really, really interesting talk. I learned a lot. So as a token of appreciation, here's a small gift.
Thank you.
And one more round of applause for Jos.
Sneller voor elkaar wil hebben voor een goede